السلام عليكم ورحمة الله وبركاته. Inshallah, in this session, we are going to talk about inference for mean. In chapter 6, we talk about inference for mean. We talk about how to construct confidence interval for mu, and also how to construct test of hypothesis and test of significance in section 6.2. Now, same, we are going to talk about inference for the population mean mu, but in a different way. Let's see the subsections. First, we are going to discuss T distributions. Before, in chapter 6, we talk or we use Z distribution and we use Z table. In this case, inshallah, we are going to use T distribution instead of Z distributions. One sample T confidence interval, same in chapter 6, we use one sample Z confidence interval because we was using Z table or Z distribution. One sample T test. Also, we are going to construct test of significance, test of hypothesis. Instead of using one sample T test, we are going to use one sample T test, not Z test. Last, we are going to match pairs T procedure. We are going to discuss all these four subsection, inshallah, in this chapter 7.1. Before, in chapter 6, when sample distribution of x bar is close to normal or approximately normal, we can find probability involving x bar by finding z. We know if x distributed normal with mu and sigma, then x bar also distributed normal with mu and sigma over square root n. Sigma over square root n. Then x bar minus mu over sigma over square root n is following a standard normal distribution with 0 and 1, with 0 and 1, and this variable is z is following a normal distribution with 0 and 1. The difference in this chapter is sigma unknown. This sigma, if sigma is unknown, in this case, instead of using sigma, we are going to use S. S. S is the standard deviation computed from the sample. So we use this statistic to estimate the parameter sigma. Why? Because sigma is unknown. So in this case, we have a new variable, which is t. We call this t equal x bar minus mu over s over square root n. This variable, this new variable, is not following z. This variable is following t. So instead of using z, we are going to use z. We are going to use t. T is have it on a PDF, but a little bit complicated. And actually, we don't need to use the function because already we have a table constructed from the function. So just we have to know how to use this, how to use the table in order to find the area under the curve. So we already discussed this before. If we have x following a normal distribution, then x bar minus mu over s over square root over sigma over square root n is following normal distribution with mu equals 0 and standard deviation equal sigma. Now we have new statistic. We call this t. This is not normal distribution. This new statistic does not have a normal distribution. Yes, it's not a normal distribution. It is a t distribution. And now let's see what is the t distribution. Standard deviation, standard error, s over square root n. We call this standard error. We call this standard error. So standard error of x bar is s over square root n over square root n. We call this standard error of x bar. Standard error of x bar is s over square root n. Now we have example, simple random sample of 5 female basketball players. Select their height in centimeter are reported here: 170, 175, 169, 183, and 177. If the question is find the standard error of x bar, s standard error of x bar, which is s over square root n. So how to find s? S is the square root of s square. S square is the variance. S is the standard deviation of the sample. We can compute it easy by using a shortcut n summation x square minus summation x all square over n minus 1. Using these values, so standard error is square root of 32.2. By using this formula, we have s is the square roots of 32.2. For computing x bar, yes, x bar is summation of this value, summation of all heights over the total number of height, which is 5. This equal 174.8. 174.8. Now we compute x bar sample mean. Also we compute standard deviation of mean, standard deviation of sample. We use this standard deviation of sample to find standard error of x bar just by dividing this standard deviation of sample over square root of n, which is 5. We got this. And this is standard error of mean, SEM, standard error of mean, which is 2.538. The t distribution, when we standardize based on the sample standard deviation. So when we use standard deviation of the sample, Sx, or even x without s without x, just we write it s. So this is computed from sample. If we use this instead of sigma, then we got a new statistic. This statistic is following T distributions. T distribution is a little bit different from a standard normal distribution. We can see the different. This is a function T equal x bar minus mu over S over square root n. Here we use sample standard deviation. Here we use population standard deviation, which was known. This was known. We use this in chapter 6.1. And now we are going to use this in chapter 7.1. Instead of using sigma, we use S. So instead of using Z, we are going to use T. So this is a T curve, and this is a Z curve. T distribution depend on a sample size. The distribution have one parameter, which is degree of freedom. So in order to use T distribution, we need to know the degree of freedom, df, degree of freedom. So T distribution value rely on the sample size. Different sample size, different T value. So let's suppose that SRS of size n is drawn from a normal distribution with mu and sigma population. When sigma is known, if sigma is known, we discussed this in chapter 6, the sampling distribution of x bar is mu sigma over square root n. If sigma is unknown, if this unknown, in this case, let's see, if sigma, if unknown, so in this case, instead of using sigma, we are going to use S. So in this case, the distribution or sampling distribution of x bar is mu S over square root n. Here, instead of using sigma, we use S. So it is mu, it was sigma over square root n plus sigma was known. If sigma is unknown, and instead of using sigma, we use S, then this distribution is not normal. This distribution is following a T distribution with n minus 1 degree of freedom. If we have example, we selected SRS of size, say 10. In this case, degree of freedom for T distribution supposed to be 9. So we need to know this because this is the parameter of T distribution, and then we can use a table. X bar minus mu over S over square root n is called the one sample T test. When we perform inference about population mean, mu, using a T distribution, the appropriate degree of freedom are found by subtracting 1 from the sample size and making degree of freedom equal n minus 1. As we mentioned before, degree of freedom for one sample T test is sample size minus 1. T distribution degree of freedom drawn a simple random sample of size n from large population that has a normal distribution with mean mu and standard deviation sigma. The one sample T statistic is sigma x bar minus mu over S over square root n. Standard deviation sigma unknown standard deviation. This is unknown. So instead of using S, instead of using sigma, we use S. This has a T distribution with n minus 1. If sigma is known, this have a Z distribution, not a T distribution. So that the only difference between Z distribution and T distribution, we call it one sample T distribution and one sample Z distribution. The only difference is For Z, we use sigma because sigma known, and for T, we use S instead of sigma. Let's compare the density curve of the T and the density curve of T distribution are similar. Both have bell shape. Separate spread of the T distribution is a bit larger than that of standard normal distributions. So T distribution look like a bit large than standard normal distribution. T distribution have more probability in the tails. So in the ends, both ends uh, have more probabilities and less in the center than does the standard normal. As the degree of freedom increase, this is the important properties. As the degree of freedom increase, the density curve become ever closer to the standard normal distribution. That's why we find if n equal 120, if n 120, in this case, instead, we can use both T or Z. 120, because T table, the lark in T table is 120. So as n increase, as T distribution become more close to standard normal distributions. We can use table D in the back of the book. Already we have the this table in Blackboard with other table called statistical tables. Now let's see how to use this table. We know how to use the standard normal. Now we are trying to know how to use T table. Here we have a sample distribution of X bar when sigma is unknown, and instead of sigma we use S. It follow a T distribution. It follow a T distribution with mu and S over square root n with m minus 1 degree of freedom. The distribution of X bar minus mu over S over square root n is following a T distribution also with n minus 1 degree of freedom. So it's distribution of X bar, and this distribution of X bar minus mu over S over square root n. Suppose we want to construct 95 confidence interval for the mean mu of a normal population based on SRS of size n equals 12. What is the critical T star should be used? Okay, let's see. When we use same as we use in chapter 6.1, when we construct 95 confidence interval for the mean, just we write like supposed to be X bar plus or minus marginal error, called it M. This marginal error is X bar plus or minus Z star multiplied by sigma over square root n. Just reminding you, when sigma is known, we use Z. This was X bar. If we use 95 confidence interval, Z is 1.96. multiply by sigma. Sigma is known. We have the value of sigma. We divide this over square root of n, which is 12. This if this confidence interval or 95 confidence interval when sigma is known. Sigma is known. Okay, 95 confidence interval. If sigma is unknown, it's almost same x bar plus marginal error, plus this marginal error is, instead of z, we are going to use t star. Instead of sigma, we are going to use s over square root n x bar plus or minus. We need to find the t. So just like this, of course, when sigma is unknown. Okay, now how to find this t, critical value of t? Here we have 95 confidence interval. Let's see, here we have 95 confidence interval, which is this is 95. This is, okay, this is 0.95. This is 0.025. This is 0.022. We need to find this value of t and this value of t. So here we have 0.025 and degree of freedom is m minus 1. M minus 1 is 11. So we go to the table. We call this label of significance, and we call this degree of freedom. So we go to the table and find the value corresponding to 11 and 0.025. In general, for a confidence interval, it's like t alpha over 2, alpha over 2, and m minus 1. M minus 1. Here, 1 minus alpha is 0.95. Alpha is 0.05. Alpha over 2 is 0.025. That's why we use 0.025. We go direct to the table, this first column, just like Z column, this degree of freedom column. We go to 11, this 11, and we go to the row column 0.025. This intersection of this is a value of t. So here t star we use 2.2, 2.2, 2.201. Instead of sigma, we use s over root n, which is 12. So how to find s from the sample and how to find x bar also from the sample. So this is critical value of t. The one sample t interval for the population mean, we already discussed this. It's x bar plus or minus t star s sx over square root n. We know how to find this degree of freedom and alpha over 2, x bar computed from the sample, s also computed from the sample, and square root of n is square root of the sample size. Let's take example. On average, UK subscriber with 3G phones spend an average of 8.3 hours per month listening for full track music on their cell phones. Suppose we want to determine a 95 confidence interval for the average and run the following random sample of size 8. So 8 sample size from the population of 3G subscribers. Uh, Same, actually here, sigma is unknown. So we need to construct 95 confidence interval. This 95 confidence interval is not same like what we see before. It is 2.201. This we use it with, yes, 95, but n was 12. Now we have different n. N here is 8. So definitely we are going to get a different value of t stars. Okay, let's see. For t, we are going to alpha over 2.025 and n minus 1 is 7. So we go to the table and see this value. Then we compute x bar, summation of x over n. Also we compute s, square root of s squared, which is square root of n, summation x squared minus summation x all square over n minus 1, n minus 1. Compute these values. So we already got x bar is equal 5, and we got this equal 3.63. So now 95 confident interval for mu is x bar plus or minus t star, we got it from table, multiplied by s over root n. X bar is 5, t from table, let's see this from table. S already we got S is 3.63. Square root of n is the square root of 8. So just we need to find the value of t. We go table and we find the value of t. 7, degree of freedom is 7. Alpha over 2 is 0.025, this value. So this one, this one, 3.265. So we just write 3.2, this value 3.265, 2.365, 2.365. So we write here 2.365. 3.63, which is s over square root 8. This is a confidence interval, 95 confidence interval by using a one sample t test instead of z. which is this one. We have other example, manufacture of high resolution video terminals must control the tension of the mesh of fine wires that lies behind the surface of the viewing screen. The tension is measured by electrical devices with output reading in millivolts. A random sample of 20 screen has the following mean and standard deviation. X bar is given, S is given. We want to estimate the true mean tension mu of the video terminal produced this day at 90% confidence level. So we have X bar, we have S, we have N, this N equal to 20. We need to find, because standard deviation is unknown here. So instead of using Z, we are going to use T. T with, here we have 1 minus alpha equal 0.9. Alpha equal 0.1. Alpha over 2 equal 0.05. So we are going to use, because we talk about confidence interval means two sides. That's why we divide it over 2. So degree of freedom is m minus 1. M minus 1 is 19. So for T, we go to the table and see T with 0.05 level of significance and 19 degree of freedom from the table. We see this value. Then just we come to use confidence interval is X bar plus or minus T star multiplied by S is already given, this S over square root n already given, which is 20. So just we need to find the value of, from the table, we go, this is 19. This is 0.05 because we are using 90%. So this is the value of T star. So just we use X bar is 3066.32 plus or minus T star already 1.729 multiplied by S. S is 36.21 over square root of n, which is 20. This is 90 confidence interval for the mu. This is a confidence interval for the mean. This means 90% confident that the interval from 292.32 to 320.32 captures the true mean tension in the entry patch of video terminal produced that day. This is a definition of the confidence interval, actually. Assume that you don't know what's the population standard deviation. So sigma unknown, this is the first information. Unknown. You drawn sample of 30. So here we have n equal 30, n minus 1 is 29. The mean of your sample is X bar. X bar is standard deviation for our sample is S equal 0.4. What is the 98 confidence interval for the population mean round your answer to true decimal places. In this case, first we need to find t. So to find t here, we have 1 minus alpha. So confidence interval is 0.98. Alpha is 0.02. Alpha over 2 is 0.001. So this is alpha over 2. We need to go to the table and see this value. Okay, from the table, D of 0.01, not 0.01, it's 0.01 plus 0.01, and 29, 29's degree of freedom is equal to 2.7 to 2.7, 2.756556. So this is the from the table is 2.756. Now 98 confident interval, 98 confident interval for the mean is x bar already computed 4.8, 4.8 plus or minus. We already got t is 2.756 multiplied by sigma. Sigma is s 0.4 over square root of n, which is 30. Yes, we use calculator to find the upper and the lower value for this confident interval. So confident interval, 95 confident interval is 4.8 plus or minus 2.756 multiplied by 0.4 over square root 30. This is the first section in chapter 7, talking about how to construct a confident interval when the standard deviation of a population is unknown and we estimate it by S, and instead of using sigma, we use S. Sorry, instead of using sigma, yes, instead of using sigma, we use S, but instead of using Z, we use the distribution because this new statistic is following the distribution, not Z. Now, the section 2 is talking about one sample t-test, test of hypothesis. As we done as in the previous chapter, a test of hypothesis require a few steps. First, we need to state the hypothesis. We need to state the H naught and HA. And we talk about this, how to state H naught and how to state HA. Then we need to calculate the T and its degree of freedom. Actually, we need to calculate the T tabulated from the table. And also we need to calculate T statistics from the information. We use this statistic, test statistics. This is a test statistic. Before we was using Z, now we are using T. T is x bar minus mu naught over S over square root n. So this is supposed to follow a normal T distribution with m minus 1 degree of freedom. So we need to compute this value, and we use this value to compute the p-value. Then we compare p-value with alpha level of significant, and then we decide to reject or to fail to reject epsilon. Same procedure we used before in section 6.2. We are going to use, just instead of using the one sample Z test, we are going to use one sample T test. Let's see. Same like before, we have three cases. Case one, this case one, this case two, and this case three. This we call this one side, and this two side. This is a T calculated. We call this T calculated because we calculated this from the sample. We call this T calculated or T cal. Then we use T tab. We find T tab according to degree of freedom minus n minus 1. And for the one side, we use alpha and n minus 1. Is T tabulated. Also here T tabulated is alpha or n minus 1. Here we use T tabulated alpha over 2 because these two sides, the same like confidence interval. By the way, also you can use confidence interval, same. And we see if mu naught inside this, we fail to reject. If mu naught fell outside of this interval, then we reject H naught. We already discussed and talk in this about these three cases and how to decide whether to reject or not to reject or fail to reject H naught. We call this case one, this case two, and this case three. So here we can compare T calculated with T tabulated. If T calculated greater than T tabulated, we reject H naught. Here, if T calculated less than T tabulated, we reject H naught. Here also, we compare T tabulated with T calculated, and then we decide to reject or this easy way. The second way, we compare alpha level of significance with p-value. How to find p-value? We find p-value by using T calculated. Instead of comparing T calculated with T tabulated, we use T calculated to find p-value, and then we compare p-value with alpha. Let's see example. P-value is calculated as the corresponding area under the curve. Yes. This is the three cases. This is the test. Here we have example. The level of dissolved oxygen DO in stream or river is an important indicator of water ability to supply aquatic life. A researcher measures the DO level at 50 random chosen location along stream. Here are the results in milligram per liters. A dissolved oxygen level below 5 means life at risk. So how to state the null hypothesis and the alternative hypothesis. Actually, researchers like to prove or like to, his claim is life is at risk. So life at risk means DO is less than 5. So it's not will be life is not at risk. So it's not is mu equal 5. Life is not at risk. And HA is life at risk. we use alpha equal 0.05 is given. It's supposed to be given before. طيب, now we have alpha 0.05. We have this case 1. We need to compute t statistics, and also we need to compute t tabulated. We can compare t tabulated with t calculated. Let's see, we already compute x bar s, then we can compute the test statistic t calculated is minus 0.94. We can use this value to find the b value. Let's start with comparing b value with alpha. We know if b value greater, if b value less than alpha, then we reject h naught. Okay, so we use this value of t calculated to find the p value. So we have 0.94, 0.94. We have degree of freedom equal 14, so we go to 14 and try to find this value. This value, we don't have this value exactly, but this value is supposed to be between these two values. Supposed to be between these two values. It's 0.2, between 0.2 and 0.15. Less than 0.2 and greater than 0.15. So here we use why we use plus table. Actually, the table just right from the right, but t less than minus 0.95, it's same like t greater than 0.94 because it is symmetric. It is symmetric. So this value, also we can be in this side. It is same. It is same. So we are trying to find this area. This area, of course, area less than minus 0.95, same like area greater than 0.95. So b value is supposed to be between these two values. Let's say 0.175. 0.175. Let's say 0.175. Compare this with alpha. Alpha is given 0.05. Even 0.2, even 0.2, or even 0.15, this value is, this p value definitely is greater than alpha equal 0.05. So we fail to reject the epsilon. Fail to reject the epsilon. Fail to reject epsilon. And we don't have enough evidence to conclude that the mean DO level in the stream is less than, so we don't have evidence to conclude this life is at risk. We don't have evidence. This is the one procedure that we use alpha and compare alpha with p value. P value we compute it after we compute the statistic. We have other methods, which I think is a little bit easier than this. Here we already compute the statistics. We need to compute this T calculated, of course. We need to calculate T tabulated, T tab from the table with alpha already 0.05, and degree of freedom is 14. We go to the table and see this value, and then we see how to use this value to decide about the null hypothesis. Okay, this value from table is equal minus 1.7617661. So is if it's not is true, is supposed to be this value is minus 1.761. So minus 0.94. Is it here or here? This here is supposed to be in this. Minus 0.94 is right to this value. So this value is inside this acceptance region, not in rejection region. So we fail to reject H naught. So we can compare p value with alpha. If p value less than alpha, reject H naught. Or we can compare for this case, case one, T calculated, T cal less than T tab. We also reject H. Otherwise, we fail to reject H naught as in our case. In our case, p value is greater than alpha, and T calculated also is greater than T tabulated, so we fail to reject H naught. Both methods give same result, definitely. Now we are going to the last part of the class, matches pairs T procedures. We use this method to compare, like we compare two measures of same samples. For example, in pre-year, we used to give pre-test, placement test, and post-test. And then we give this at the beginning of semester, at beginning of when you come to preschool, pre-university. We give this pre-year. We give you placement test. After first semester, we give a student a post-test, and then we try to compare whether student performance increase or not. So let's see how to use this procedure. Here we have cola manufacturer want to test how much sweetness of new cola drink is affected by storage. The sweetness different to use storage was evaluated by 5 professional testers by comparing the sweetness before and after. Always like before and after. So we want to check whether storage effect or not. If no effects, this means D equals 0. No difference. No difference. So the procedure is like this. We compute difference of each case. This case 1 or instance 1, individual 1, we find the difference before storage and after. We find the difference before minus after. This before minus after. Before minus after. For all, for the 10 item, before and after. We compute this. Now we are trying to study this. This is the difference. We study the difference. It's not always is like, it's not is no different. Mu not equal 0. So no different. It's A is exist different. Exist different. In this case, 2. We try to find the test statistic, T like before, is X bar of this. Let's say D bar, difference bar, compute this, summation over N, summation of difference over N. We compute this value, equal this D bar, minus, of course, minus 0. So we just, okay, minus 0 over S of D bar, we find S of this. Just we treat this or we use this as a sample. This is our sample. Our sample is the difference between before minus after over S of what? S of difference over square root N. Then we do same as we did before. We compare this T statistic with the T tabulated. If T statistic, because case 2, if T statistic, if T calculated greater than T tabulated, we reject H naught. T tabulated, we need to know degree of freedom we have. Degree of freedom is 9, but we want to know the level of significance. If level of significance is 0.05, then we find 0.05 and 9. We find this and compare this with the T calculated by using this test statistic. Or we can use, after we compute the T statistic, we use this T statistic to find the B value. Then this B value compare with alpha. If T value less than alpha, we reject H naught. So if T value less than alpha, we reject H naught. Or if T calculated is greater than T tabulated, we also reject H naught. Otherwise, we fail to reject H naught. Let's see, have other examples. Individual diagonists as caffeine dependent are assigned to receive daily pills. Sometimes the pills contain caffeine and other times they contain a placebo. Depression was assessed for each individual in the sample. We have calculated a difference in depression score. Placebo minus caffeine. So we have 11 individuals. We calculate the difference. Is depression with caffeine and without caffeine. Compute the difference between depression with placebo is fake. Yeah, like no caffeine, nothing. And this with caffeine, and then we find the subtract 16 minus 5 is 10, 23 minus 5 is 18, 5 minus 4 is So H naught is a caffeine or depression not affected with caffeine. No difference. No difference is 0. Here we have difference. Different is mu difference greater than depression with placebo greater than depression with caffeine. Let's see. First, we need to compute the test. We have degree of freedom equal 10. We have x bar. Actually, we use the difference. We don't use this. So just we use this. We use the difference. We use this difference. And just like one sample t-test from here, from this difference, we compute the x bar of difference. We compute s of difference. This is x bar of difference, and this s of difference. Then we compute test statistics, x bar over s over square root n equals this. Then we go to the table to compute t with alpha over 2 alpha. Let's see alpha. Alpha is 0.005 degree of freedom. They have to mention alpha somewhere. Alpha alpha. I think they use alpha equal 0.005. This level of significance. This have to be mentioned in advance. But let's see alpha equal 0.05 from the table. We go to T table T and check 0.005 and 10. We find the T value is 3.169. So we can compare this value with this value. Since this value is greater than T calculated, greater than T tabulated, greater than T tab, which is 3 point, which is 3.16, which is 3.169. So we reject H naught, which is different equal 0, no different, no exist a difference, and caffeine cause significant increase in depressions. Caffeine cause increase in depression. Why? Because T calculated is greater than T tabulated. Also, we can compare B value with we compare T value. We compare B value. B value is between 0.005 and 0.025. So P value is greater than 0.005. So it's same if P value is greater. In all cases, if P value is greater than alpha, we we reject H naught. Here P value is less than 0.005, so reject H naught. The problem in T, we not easy to find B value exactly unless we use online calculator for finding B value. But from table, It's not the exact p-value, not like z-table. Z-table, we find exact value of p-value, but here p-value is greater than 0.025, but less than 0.005. Since p-value is less than 0.005, we reject H naught. Reject H naught. Reject H naught. Major MELT 3D multi-sensor metrology software is used to various companies to measure complex machine parts. GE Healthcare discovered that unchecking one software option reduced measurement time by 10%. To further investigate this, the researchers measured 51 part using the software both with and without option checked. Order for checking the option or not was randomized. The difference in measurements with the option check and uncheck was recorded. We want to perform the test alpha equal 0.05. This alpha is known in advance, 0.05 significant level. H not no different. H A alternative hypothesis exists a difference or no difference. So this is two-side test. This case 3. This last case. By the way, this test exactly can be done by using confidence interval of mean. Just we try to find the confidence interval and see whether 0 is inside. We can find the confidence interval and see whether 0 is inside this or outside. If inside, we fail to reject H naught. If outside, we reject H naught. How to construct? We know how to construct which is T star from the table multiplied by S over square root N. So we need to find we have X bar, we have S, just we need to find the T. Can find T from the table, and then we can construct the confidence interval and find whether 0 is inside this interval or not. S over square root N. Yes, we need to find this with M minus alpha over 2 is 0.025, 0.025, and degree of freedom 51 minus 1 is 50. We find this from the table. Already we have X bar and we have S. Okay, so we can find that this is the other method. We find the test statistics, which is 0.52. So we use this value to find the b value from the table. Let's see, we have 50 degree of freedom, and we need to find b value of 0.52. 0.52 is supposed to be here. So b value is supposed to be greater. Actually, b value is 0.3 0.27027 exactly. Let's say it's 0.327, but 0.3 is the v value, because we have we have two side test. So we multiply this value with 2 or divide this value over 2 and then compare it with alpha. Multiply this with 2, get 0.6. 0.6. Compare this with alpha. Alpha is 0.05. Definitely this value is greater than alpha. So we fail to reject H naught. Also, we can compare this value by alpha over 2. This value is 0.3. Compare this by alpha over 2, which is 0.025. Same, we fail to reject H naught because p value is greater than alpha. Since p-value is greater than 0.025, we use 0.025, but actually 0.25, but actually it is greater than 0.2. Actually, it's 0.3 from the online calculator. But here, definitely this is supposed to be greater than, but even if we use this, even if we use 0.25, also this value is greater. Even 0.5 is greater than 0.05. So we fail to reject H naught. We don't have enough evidence to conclude that unchecking the option has impact on the measurements time. We don't, but just as homework, try to find the confidence interval for the mean and use the confidence interval to construct the test. Does 0 inside this interval or not? And we done for 7.1.